Tonight, I have to begin with a confession about the title of this video. It is wrong. It is not wrong in the direction you might hope. In the 4 or 5 seconds it took you to read that title, the number of ghost particles that passed through your body was not trillions. It was hundreds of trillions. Every second of your life, awake or asleep, about 100 trillion particles called neutrinos pass through your body. Through your skin, your bones, your heart, your brain. They do not slow down, they do not swerve. I said, most of them entered through one side of the earth, passed through the entire planet as if it were not there, passed through you as if you were not there, and continued on into space, and not one of them, in your whole life, will leave a mark. Hold up your thumb. Right now, about 65 billion neutrinos are passing through your thumbnail every single second, almost all of them made in the core of the sun 8 minutes ago. At night, they come up through your mattress, through the planet itself, because to a neutrino, the Earth is barely an inconvenience. You are, at this moment, standing in the heaviest rain in the universe, a downpour that has never stopped since before the Earth existed, and you have never felt a single drop. Tonight is the biography of that rain. It is the life story of the strangest character in physics, a particle that was invented out of desperation before anyone believed it could exist, that its own creator apologized for, that took 26 years to catch, that turned out to be the second most common particle in the universe, that changes its identity while it flies, that passed through your body by the trillions from a star that exploded before humans built cities, and that may, before this story ends, turn out to be the reason anything exists at all. Physicists call it the ghost particle, and for once, the nickname undersells the truth. Before we meet it properly, if you enjoy these long, quiet journeys through the deep universe, a like or subscribe genuinely helps this channel grow. It is a small thing for you, and it means everything to me. Now, let's begin. Every biography should start before the birth, with the world into which its subject arrived, so let us go to that world, physics at the end of the 1920s, a field that had every reason to be proud of itself and one very good reason to be terrified. The pride came from a golden decade. Quantum mechanics had just been built, atoms were finally understood, and it seemed the basement of nature was nearly mapped. The terror came from a single, stubborn experiment, and to understand it, you need only one idea, the most sacred idea in all of physics: energy is never created and never destroyed. It only changes form. This law of conservation had survived every test ever thrown at it. Engineers built centuries of machines on it. It was not a rule of physics, it was the rule, the one commandment nature had never once been caught breaking. And then radioactivity was discovered, and one particular kind of it began to misbehave. Certain unstable atoms decay by spitting out an electron. The process is called beta decay, and it is going on right now in trace atoms inside your own body, which will matter later tonight in a way I promise you do not expect. Physicists measured beta decay with increasing care through the 1920s, and the measurements returned something monstrous. The energy did not add up. The atom before the decay carried a definite, known amount of energy. The atom and the electron after the decay, added together, carried less. Not occasionally, always, and by a different amount each time, as though the missing energy were being stolen in random quantities. Some of the energy of the universe was simply vanishing in laboratory glassware on ordinary afternoons. The greatest names in physics stared at this and split into camps of quiet horror. Niels Bohr, one of the founders of quantum theory, was prepared to consider the unthinkable, that perhaps in the atomic world, energy conservation was only approximately true, that the deepest law was a suggestion. Read that again. The situation was desperate enough that the fathers of modern physics were drafting the surrender of their most sacred principle. And it is at this moment, in December of 1930, that our subject is born, not in a laboratory, but in a letter, one of the most famous letters in the history of science. The physicist Wolfgang Pauli, a man so feared for his sharp tongue that colleagues called him the scourge of God, was invited to a physics meeting in the German city of Tübingen. He could not attend. He had a ball to go to in Zurich, and Pauli was not a man who missed balls. So he wrote to the assembled experts instead, opening with the immortal greeting, "Dear radioactive ladies and gentlemen." And in that letter, almost apologetically, he proposed what he called a desperate remedy. Suppose, he said, that in every beta decay, a third particle is emitted alongside the electron, a particle nobody has ever seen. It would have to be electrically neutral, so it leaves no trail. It would have to be almost massless, or entirely so, and it would have to interact with ordinary matter so feebly that it flies out of every detector, every wall, every planet, unstopped and unnoticed, carrying away exactly the missing energy. The books would balance. The sacred law would be saved. The prize was admitting into physics a particle defined by its refusal to be seen. Pauli knew precisely how outrageous this was. He confessed to a colleague afterward, in a sentence that deserves to be carved somewhere, "I have done a terrible thing. I have postulated a particle that cannot be detected." For a theorist of Pauli's generation, this was close to sin. A scientific idea that can never be tested is not science, it is theology with equations. He reportedly wagered a case of champagne that no one would ever detect. Remember that champagne. It comes back at the end of an act, 26 years later. The particle needed a name, and it got one from the man who did the most to make it respectable. In Rome, Enrico Fermi took Pauli's desperate remedy and built it into a full, working theory of beta decay, treating the little neutral one seriously as a citizen of physics. And the little neutral one is exactly what he called it. In Italian, neutrino. The name stuck, the theory worked brilliantly, and physics found itself in the strangest of positions, in possession of a particle that explained everything and had been seen by no one, a ghost written into the laws of nature on credit. To understand why catching it took a quarter of a century, you need to feel, in your bones, what it means for a particle to barely interact, and this is the part of tonight where the numbers stop behaving like numbers. Everything you have ever touched, seen, or collided with is governed by the electromagnetic force. Light is its messenger. The solidity of your floor is its handiwork. The electrons of the floor repel the electrons of your feet, and that mutual refusal is what you call standing. Atoms announce themselves to one another electromagnetically, which is why matter, to matter, feels substantial. The neutrino carries no electric charge. None. The electromagnetic force, the great communicator of the material world, cannot speak to it at all. To a neutrino, the electric architecture of your body, all its bonds and repulsions and fields, simply is not there, the way a radio broadcast is not there to someone with no radio. The neutrino answers to only two things: gravity, so faintly it hardly counts for a particle so light, and one other force, the weak nuclear force, the shy, short-ranged interaction responsible for certain kinds of radioactive decay. And the weak force deserves its name. Its reach is about 1,000 times shorter than the width of a proton. For a neutrino to interact with an atom, it cannot merely pass nearby. It must score what amounts to a direct hit on a nucleus or an electron, a bullseye on a target that occupies a trillionth of the volume of the atom, and even then, the interaction usually declines to happen. The resulting numbers are the kind you have to say slowly. A single neutrino flying through solid lead would need, on average, about 1 light-year of lead, 9.5 trillion kilometers of it, before it had a decent chance of hitting anything. Stacks lead from here to the nearest star, and the average neutrino sails through the whole column and out the far end, untouched. Your body, 8 minutes from the sun, is not even a rounding error. Of the 100 trillion solar neutrinos crossing you each second, roughly one single neutrino will actually interact with an atom of your body every couple of years. In an entire human lifetime, a few dozen touches out of a reign of quadrillions of quadrillions. That is the creature Pauli invented and Fermi named. Not rare, the opposite of rare, the second most abundant particle in the universe after light itself, just perfectly, almost flawlessly, indifferent. The universe is full of it, and it is empty of the universe. And in 1956, two physicists finally caught one, and the way they did it is one of the great heist stories in science. The two physicists were Frederick Rains and Clyde Cowan, and their reasoning had the beautiful bluntness of a bank job. If the neutrino almost never interacts, they said, then do not chase quality. Chase quantity. You cannot make one neutrino more catchable, but if you stand in a flood of trillions upon trillions of them, then even odds of 1 in a quintillion start paying out on a schedule. What they needed was the most intense source of neutrinos on Earth, and by the early 1950s, humanity had accidentally built one, the nuclear reactor. A working reactor is a beta decay factory. Its fission products decay furiously, and each decay releases a neutrino, or more precisely an antineutrino, the particle's mirror twin, at a rate of trillions upon trillions per second, day and night, streaming out through the reactor walls unimpeded, because of course no wall means anything to them. Rains and Cowan named their effort Project Poltergeist, which tells you they had a sense of humor about hunting ghosts, and their first serious idea, which they genuinely explored, was to detect neutrinos from a nuclear bomb test, parking a detector near an atomic explosion for the sake of the flux. Cooler heads and better engineering prevailed, and they settled beneath a reactor at the Savannah River plant in South Carolina, with tanks holding hundreds of liters of water laced with a special salt, watched by light sensors. The trap was elegant, on the fantastically rare occasion that an antineutrino from the reactor scored a direct hit on a proton in the water. Theory predicted a precise two-step signature, a flash from the collision, then, microseconds later, a second flash as a byproduct was absorbed by the salt. One flash can be anything. Two flashes, with exactly that spacing, at exactly those energies, again and again, only when the reactor is running. That is a fingerprint. Through 1956, the double flashes accumulated, a few per hour, feeble and unmistakable, and every alternative explanation was strangled by careful checks. 26 years after the desperate letter, the ghost was in the tank. Rains and Cowan sent Polly a telegram in Zurich that June, and it read like the closing line of a long novel: "We are happy to inform you that we have definitely detected neutrinos." Polly, it is said, interrupted the conference he was attending to read the telegram aloud, and he and his friends finished a case of champagne. The wager was paid. The undetectable particle had been detected. Rains would eventually receive the Nobel Prize for it. Decades later, after Cowan had passed away, and physics had learned a lesson it is never forgotten, in the quantum world, never, never means never. It means, build a bigger tank. And that lesson matters, because the tanks were about to get very much bigger, and they were about to be pointed at the sky, where the neutrino's biography turns from a laboratory tale into a story about the stars, beginning with a question so simple it sounds like a child's. How do we know what makes the sun shine? Think about that question honestly for a moment. By the 1950s, physicists were confident the sun runs on nuclear fusion, hydrogen forged into helium in the core, mass converted to light. But confidence is not a sight. The sunlight that reaches your face tells you about the sun's surface, and here's a fact that never stops being strange. The light born in the sun's core takes tens of thousands of years to fight its way out. The core is so dense that a photon cannot travel a centimeter without being absorbed and re-emitted, staggering outward in a drunkard's walk of countless scatterings, so that the glow leaving the surface today carries news that is, in a real sense, prehistoric. If the sun's furnace changed today, the light would not report it in your lifetime or your civilization's. There is exactly one witness that leaves the scene immediately, and by now you know its name. Fusion in the solar core produces neutrinos directly, and to a neutrino, the crushing interior of the sun is as transparent as everything else. Each one crosses the entire star in about 2 seconds and arrives at the Earth 8 minutes later, carrying an unfiltered, real-time report from the heart of a star. Solar neutrinos are, quite literally, the only direct message we have ever received from inside the sun. So in the 1960s, a chemist named Raymond Davis decided to read the mail, and his instrument remains one of the most eccentric ever built. Deep in the Homestake gold mine in South Dakota, a mile underground to shield it from ordinary cosmic radiation, Davis installed a tank holding 600 tons of dry cleaning fluid. That is not a joke. The cleaning fluid was rich in chlorine, and theory said that on rare occasions, a solar neutrino would strike a chlorine nucleus and transform it into a radioactive atom of argon. Davis's task was to let the tank soak in the solar rain for weeks, then flush it and count the argon atoms his chemistry had captured, and the expected catch, from a tank of 600 tons sitting in a flux of trillions per square centimeter per second, was a handful of atoms per month. Individual atoms, fished out of 600 tons of fluid, roughly 10 of them in a good month, and Davis's chemistry was so exquisite he could do it, a feat colleagues compared to finding a specific grain of sand in an entire desert, repeatedly, on schedule. The experiment worked. the argon appeared, the sun's core had been observed. And with that triumph came one of the most productive crises in the history of science, because Davis's catch was wrong. Not wrong as in absent, wrong as in short. Month after month, year after year, the tank captured about 1/3 of the neutrinos that the best solar models, built by the theorist John Bockall, said it must. 2/3 of the sun's neutrinos were missing. For 30 years, this was the solar neutrino problem, and it hung over physics like an unpaid debt. The options were stark and all unpleasant. Perhaps Bockall's solar model was wrong, but it kept passing every other test, and its authors spent decades defending it with meticulous care. Perhaps Davis's chemistry was wrong, but it was checked, rechecked, and eventually reproduced by other experiments in other countries with other methods, which all found the same shortfall. Or perhaps, and this was the possibility whispered early and believed late, something was happening to the neutrinos themselves, somewhere in the 8 minutes between the core of the sun and the tanks of the Earth. Perhaps the messengers were not missing. Perhaps they were arriving in disguise. To explain the disguise, I need to introduce the neutrino family, because our ghost, it turns out, is triplets. Nature makes 3 kinds of neutrino, 3 flavors, in the language of the field: the electron neutrino, the muon neutrino, and the tau neutrino, each partnered with one of the 3 charged members of the electron's extended family. The sun's fusion produces electron neutrinos, only that flavor, and here is the crucial fine print: Davis's chlorine tank could only detect electron neutrinos. His trap was flavor blind to the other 2 kinds. So the whispered idea took shape. What if neutrinos can change flavor in flight? What if an electron neutrino, born in the solar core, does not stay an electron neutrino, but oscillates, cycling through identities as it travels, so that by the time the sun's messengers reach South Dakota, only 1/3 of them happened to be wearing the one face Davis's tank could see. The other 2/3 would be arriving on schedule, passing through the tank in their muon and tau disguises, invisible to the chemistry, missing only in the sense that a friend in a costume is missing from a party. It is a lovely idea with one enormous consequence hiding inside it. The mathematics of quantum mechanics is unambiguous. Particles can only oscillate between identities like this if they have mass. Different masses, in fact, for the different versions. A truly massless particle experiences no time, as we learned in Another Night's Journey, and a particle that experiences no time cannot change, cannot cycle, cannot do anything on the way. So, the innocent question of the missing solar neutrinos was secretly the question: does the neutrino weigh anything at all? And the reigning theory of particle physics, the Standard Model, the most precisely confirmed theory in the history of science, had already written its answer into its foundations. The Standard Model said the neutrino's mass is exactly 0. The stage was set for the tanks to grow one more time and settle it. Before the tanks answer, the family itself deserves its portrait, because the discovery that the ghost had siblings is a story of its own, and it involves the birth of a technology that would define the field. By the early 1960s, physicists suspected that the neutrino associated with the electron might not be the only kind. The electron has a heavier, short-lived cousin called the muon, discovered raining down in cosmic rays, so puzzlingly unnecessary that a famous physicist greeted it with the words, "Who ordered that?" If the muon was a genuine sibling of the electron, did it come with its own neutrino, or did all these processes share one universal ghost? The question was answered in 1962 at Brookhaven in New York by Leon Lederman, Melvin Schwartz, and Jack Steinberger, with an invention that sounds impossible on its face: the world's first neutrino beam. They slammed protons from an accelerator into a target, producing a spray of particles that decay in flight into muons and neutrinos, aimed the whole spray down a corridor, and then, and this is the audacious part, blocked it with a wall of steel more than 13 meters thick, armor assembled in part from the scrapped plates of a battleship. 13 meters of battleship steel stops everything, every proton, every muon, every fragment, everything material, except the ghosts, which pass through the wall as if it were rumor, into a detector waiting on the far side. Then the team simply watched what the neutrinos created on the rare occasions they interacted. If neutrinos were one universal type, their collisions should have produced electrons and muons in equal measure. Instead, the detector recorded muons, almost exclusively, dozens of muon events, and essentially none of the electron kind. The ghosts remembered their parentage. A neutrino born alongside a muon makes muons. It is a distinct particle, a second flavor, and with that experiment the family structure of matter, the pattern of generations that would become the backbone of the Standard Model, snapped into view for the first time. The three physicists received the Nobel Prize, and their battleship Waltrick, making a beam of ghosts by stopping everything else, became the standard instrument of the field, the ancestor of every accelerator neutrino experiment running today. The third sibling took far longer. Theory demanded it from the 1970s, once the tau particle, a third and even heavier cousin of the electron, was discovered. But the tau neutrino is fiendish to catch in the act, because proving its identity requires seeing it produce a tau, and the tau lives for a trillionth of a second and travels only a millimeter before dying. Not until the year 2000, at Fermilab near Chicago, did an experiment with the fitting name donut photograph in special emulsion films, that telltale millimeter, a track that travels, kinks, and continues as something else, the signature of a tau born and dying, and with it the family portrait was complete. 3 charged siblings, electron, muon, tau, and 3 ghosts to match. Complete and, as measurements at particle colliders later confirmed with beautiful indirectness, closed. The decay behavior of certain particles depends on how many light neutrino types exist for them to decay into, and the measured answer is 3, exactly 3, no light fourth sibling hiding in the pattern. Why 3? Why this rhyme of generations, each heavier than the last, each with its own ghost? Nobody knows. It is one of the deepest unexplained regularities in nature, the universe writing its matter in triplicate for reasons it has declined, so far, to give. The neutrino family is the faintest copy of that triplicate, and, as we were about to learn from the mountain in Japan, its members do not respect the boundaries between themselves at all. The tanks that settled it were built on opposite sides of the world, and they are 2 of the most beautiful machines our species has ever made. The first is in Japan, a kilometer inside a mountain, and it is called Super Kamiokande, a cylindrical cathedral of stainless steel, taller than a 15-story building, filled with 50,000 tons of water so ruthlessly purified that it is among the clearest liquids on Earth, so clear that light can cross the full width of the tank and barely dim, and, engineers discovered, so pure that it slowly dissolves metal tools left in it. The walls of this cathedral are lined with more than 11,000 golden eyes, photomultiplier tubes, each a half-meter bubble of glass so sensitive it can register a single photon, the smallest possible unit of light. When a neutrino, one in the endless quadrillions, finally scores a hit on the water, the struck particle recoils faster than light travels in water, which is allowed. Nothing outruns light in vacuum, but in water, light itself is slowed, and a particle that beats it produces the optical equivalent of a sonic boom, a cone of faint blue radiance called Cherenkov light, expanding through the dark like the wake of an invisible boat. The golden eyes catch the ring of blue where the cone meets the walls, and from the ring's shape, sharpness, and timing, the physicists read the intruder's energy, its direction, and, crucially, its flavor. In 1998, Super Kamiokande announced the first decisive evidence, studying neutrinos made by cosmic rays striking the atmosphere. It found that muon neutrinos coming up through the Earth, having traveled thousands of kilometers, were arriving in visibly short supply compared to those coming down from directly overhead, having traveled only tens of kilometers. Same source, same physics, different journey lengths, different counts. The neutrinos were changing en route. The longer the road, the more of them switched costumes. Oscillation, caught in the act, the second machine, in Canada, closed the case completely, and its elegance still gives physicists goosebumps. The Sudbury Neutrino Observatory, 2 kilometers down in an active nickel mine, filled its sphere not with ordinary water, but with 1,000 tons of heavy water. Water whose hydrogen carries an extra neutron, a substance so specialized that the experiment borrowed its supply, worth hundreds of millions of dollars, from Canada's national reserves. Heavy water gave the detector a superpower no one else had. It could count solar neutrinos 2 ways at once. One kind of reaction in heavy water responds only to electron neutrinos, the sun's original flavor. Another responds to all 3 flavors equally, costumes and all. So the same machine, watching the same sun, could ask both questions simultaneously. How many messengers still wear their birth flavor, And how many messengers are there in total? In 2001 and 2002, the answers arrived. The electron flavor count matched Davis, about a third of the prediction. The all flavor count matched Bacall's solar model almost perfectly. The full expected flood was arriving, every messenger accounted for. Nothing was missing. Nothing had ever been missing. The sun had been vindicated, Davis had been vindicated, Bacall had been vindicated, and the neutrinos had been caught doing the one thing the standard model said they could not do. They oscillate, therefore they have mass. Therefore, the most successful theory in the history of physics is incomplete, and the first crack in its foundation was found not by a giant collider smashing matter at the energy frontier, but by patient people in mines, counting ghosts. The Nobel Prizes followed, for Davis and for the leaders of Super Kamiokande and Sudbury, and the solar neutrino problem, 30 years of quiet crisis, entered the textbooks as one of the great examples of how science is supposed to work. An anomaly, defended by careful people against decades of doubt, turning out to be a message from beyond the known laws. The ghost had delivered its first revelation about the deep structure of reality. It was not done. 11 years before Sudbury's answer, the neutrino had already shown humanity something else. On a single night in February 1987, and this is the chapter of the biography where the ghost becomes an astronomer. On the 23rd of February 1987, in a galaxy next door to ours, the Large Magellanic Cloud, a blue supergiant star, reached the end of its fuel and collapsed, and its death produced the brightest supernova seen from Earth in almost 4 centuries, the first since the invention of the telescope to be visible to the naked eye. Astronomers named it SN 1987A, and its light reached us after a journey of 168,000 years. But the light was not the first messenger. Roughly 3 hours before the first photons of the explosion arrived, 3 neutrino detectors around the world, in Japan, in the United States, in Russia, none of them built for astronomy, all of them underground tanks minding their own business, each recorded a sudden, silent cluster of events. Kamiokande in Japan caught 11. A detector in Ohio caught 8. A Russian instrument caught 5. 24 neutrinos, arriving together in a burst lasting about 13 seconds from the direction of the Large Magellanic Cloud. 24 sounds humble. Now hear the number behind it. For those detectors to catch 24, given how nearly uncatchable neutrinos are, the burst sweeping through the Earth had to contain, in total, around 10 billion trillion neutrinos, a 1 followed by 58 zeros, released in seconds as the star's core collapsed. During those 13 seconds, that single dying star, in its neutrino output alone, briefly outshone the light output of the entire observable universe. Every galaxy combined, and nearly all of that unimaginable flood left the wreck not as light but as ghosts. Here is the part I want you to feel personally. That burst did not only pass through the detectors, it passed through the Earth. It passed through everyone. During 13 quiet seconds in February 1987, something like 100 trillion neutrinos from a star that died before modern humans left Africa passed through your body if you were alive, or through your parents if you were not, and nobody on Earth felt a thing. The wall between you and the deaths of stars is not distance. It is only interaction, and for the ghost, there is no wall at all. The 3-hour head start, by the way, was not a violation of any speed limit. The neutrinos and the light both travel at essentially the speed limit of the universe, but the neutrinos left on time and the light left late, delayed inside the exploding star, since, as always, light must fight its way through matter and neutrinos simply excuse themselves. 24 ghosts, and they carried a library, their timing and energies confirmed, in one stroke, the broad theory of how giant stars die, decades of astrophysics validated by 13 seconds of data. And they founded a science. That February night is regarded as the birth of neutrino astronomy, the art of studying the universe not by its light but by its ghosts, and it planted a question that would take 3 more decades and a cubic kilometer of Antarctic ice to answer. If neutrinos can carry news from a dying star, what else in the universe is writing to us in this ink, and how big a mailbox would we need to read it? The mailbox they built is, by volume, the largest scientific instrument on Earth, and it is made of the planet itself. At the geographic South Pole, beneath the research station, engineers spent 7 Antarctic summers drilling holes 2.5 kilometers deep into the ice cap, using hot water as the drill, and into each hole, they lowered a string of basketball-sized glass eyes before the ice froze shut around them forever. 5,160 sensors, frozen permanently into a cubic kilometer of the clearest solid on Earth. Ice compressed by 100,000 years of pressure until its bubbles vanished, ice more transparent than diamond. The instrument is called Ice Cube, and its detector is the glacier. When a high-energy neutrino, once in a great while, strikes an atom in the ice, the collision products streak through the dark, trailing that same blue Cherenkov glow, and the buried eyes watch it pass and reconstruct the visitor's path and power. Ice Cube does something almost cheeky. Besides, it uses the entire Earth as a shield, looking down through the planet at the northern sky, because only neutrinos can arrive from below. Every other particle is filtered out by 8,000 miles of rock, the one cosmic messenger for which our whole world is a clean window. And, with this frozen eye, humanity finally began reading the universe's high-energy mail. In 2013, Ice Cube announced neutrinos of astonishing energy arriving from deep space, particles carrying, in a single subatomic package, thousands of times more energy than our largest accelerator can impart, ghosts hurled from engines somewhere in the cosmos that we had never identified. The two most energetic early arrivals were nicknamed Bert and Ernie. The physicists, like rains before them, know that ghost hunting deserves a little comedy. Then, in September 2017, a single neutrino changed astronomy. Ice Cube caught a particularly energetic arrival, and, within seconds, its automated systems calculated the incoming direction and sent an alert to the world's observatories. Look here. Telescopes swung, in space, and on the ground, and there, precisely along the ghost's arrival line, they found a blazar in flaring outburst, a galaxy 4 billion light-years away, whose central supermassive black hole fires a jet of matter at nearly light speed, and by cosmic accident, aims that jet directly at Earth. The neutrino had flown 4 billion years down the barrel of that gun, through galaxies, through gas, through everything, and ended its journey in a glacier at the bottom of our world, and in doing so, it answered a century-old question, identifying such jets as sources of the universe's most violent particle acceleration. One particle. One line drawn across 4 billion light-years. Astronomy had gained a new sense, and the ghost had a new job title, messenger from places light cannot leave. Because that is the deep promise of neutrino astronomy. Light, for all its glory, is a fragile witness. It is absorbed by dust, scattered by gas, imprisoned by dense matter, blinded near black holes. The neutrino walks out of everything. It escapes the cores of exploding stars, the throats of black hole jets, the hearts of hidden engines wrapped in dust that no telescope will ever pierce, and it arrives here carrying its birth certificate unaltered. We have begun, in this century, to see the universe the way a ghost sees it, and the sky, viewed in that light, is only beginning to open. And now the biography must come home, because I promised at the start that this story would turn out to be personal, and it is time to collect. You are not merely transparent to the neutrino rain, you are part of the weather. Your body is radioactive. Gently, harmlessly, but genuinely, among the potassium your nerves and muscles cannot live without, a tiny fraction, about 1 atom in every 10,000, is potassium-40, an unstable isotope left over from the supernovae that seeded the Earth, and it undergoes beta decay, the very process that started this whole story in 1930. Every time one of those atoms decays inside you, it emits a neutrino. The rate for an average human body is about 4,000 to 5,000 decays every second, which means that you, personally, are a neutrino source, broadcasting several thousand ghosts per second, around 350 million per day, in every direction, through your walls, through your neighbors, through the planet, outward into space forever. Some of the neutrinos you emitted as a child are now more than a light decade away, sleeting through alien systems, utterly beyond recall, the most permanent thing you have ever made. Every person you have ever hugged has passed a few of their neutrinos through you, and you through them, a silent exchange written in the universe's faintest ink. And your body is only one line in a ledger of sources that surrounds you tonight. The sun, of course, owns the daytime and the nighttime alike, 65 billion per second through every square centimeter, up through the floor after dark. The Earth beneath you is a neutrino lantern too, the slow radioactive decay of uranium, thorium, and potassium in the planet's rocks. The heat engine that helps drive the continents emits a steady glow of geoneutrinos, and detectors in Italy and Japan have actually measured that glow, using ghosts to take the temperature of the planet's interior, a kind of X-ray of the Earth taken from inside. Nuclear reactors on every continent add their artificial rivers. Cosmic rays striking the upper atmosphere produce a constant drizzle overhead. Supernovae in our galaxy, statistically due a few times per century, will each deliver their 13-second flood. And beneath all of these, oldest and quietest of all, there is a sea. Just as the universe is filled with the afterglow of light we spoke of on another night, it is filled with an afterglow of neutrinos, the cosmic neutrino background, ghosts released 1 single second after the Big Bang, before atoms, before light was free, when the newborn universe became transparent to neutrinos, long before it became transparent to anything else. They have been streaming, essentially untouched, for 13.8 billion years, and cosmology's equations place their density, today, at about 336 in every cubic centimeter of space. Every cubic centimeter. Which means that inside your body tonight, there are, at this instant, tens of millions of neutrinos that are older than the stars, older than the elements, older than light itself in any free form, relics of the universe's first second, resting briefly in the space your heart occupies before drifting on. They are the oldest unaltered things in existence, and they are inside you right now, and no instrument ever built has managed to detect even one of them, though physicists are trying, and the effort is considered one of the great prizes of the coming century. You have spent your whole life swimming in the first second of the universe. It simply never announced itself. One small domestic postscript belongs in the ledger of sources, because audiences always ask about it, and the answer is a gift to anyone who enjoys strange, true facts. Yes, bananas. A banana is rich in potassium, and so carries its tiny share of potassium-40, which means every banana on Earth is a faint neutrino source, emitting roughly 1 million neutrinos per day from the fruit bowl, along with the occasional antimatter particle from the same decays, which promptly annihilates harmlessly inside the fruit. Physicists have even coined an informal unit, the banana equivalent dose, to help the public calibrate tiny amounts of radioactivity against the utterly harmless baseline of a piece of fruit. None of this makes bananas dangerous. It makes the universe honest. Radioactivity is not an invention of industry, and the neutrino rain is not confined to laboratories and dying stars. It rises from the soil, from granite countertops and Brazil nuts, from the potassium in seawater, from your cat, from you. The lesson of the fruit bowl is the lesson of the whole biography in miniature. The extraordinary is not somewhere else. The most elusive particle in existence is being manufactured right now in your kitchen by breakfast. Add to the ledger, finally, the neutrinos of human ambition, because our species has begun, in its small way, to imitate the stars. Every major accelerator laboratory now brews its own rivers of ghosts on demand, aimed through the planet at detectors hundreds of kilometers away, and the geometry never fails to delight newcomers. There is no tunnel between the source and the detector, and there never needs to be. The beam is simply pointed downward at the correct shallow angle and fired into the ground, courting through the rock of the Earth like a needle through an apple, emerging precisely at the far laboratory, having ignored a country's worth of geology in between. Switzerland to Italy, Illinois to Minnesota, the east coast of Japan to the mountains of its interior, the ghosts commute beneath cities and farms and sleeping households by the trillions per second, and no one above ever knows. Which brings the biography to its unfinished chapters, the ones being written right now, and they are, if anything, stranger than everything that came before, because every question the neutrino has answered has opened 2 more, and the open ones cut to the foundations of existence. Begin with the mass. We know, since the oscillation discoveries, that neutrinos weigh something. We still do not know what. No experiment has ever managed to weigh a neutrino directly. The measurements so far only fence the answer in, and the fences say something absurd. The neutrino is at least 1 million times lighter than the electron, itself the featherweight of ordinary matter. If an electron were a cargo ship, the neutrino would be, at most, a coin on its deck. Nothing else in the family of matter particles is remotely like this. The others range over a factor of a few 100,000, and then the neutrino sits below them all by a further factor of 1,000,000, as if it belongs to a different economy altogether. Many physicists suspect exactly that the neutrino's freakish lightness is a clue, a seesaw, in the language of one favored theory, whose other end rests on physics at energies near the scale where the forces themselves may unify, making the lightest known particle of matter a whisper from the heaviest undiscovered ones. Measuring that mass is now a dedicated industry. In Germany, an instrument called Cautrin, built around a spectrometer so large it had to be shipped 9,000 kilometers by river and sea because it could not fit through the roads of the country that built it, is weighing the ghost by examining beta decay, Pauli's original crime scene, with the finest energy resolution ever achieved. The fences are closing, the number is still out. Then there is the question of the mirror. Every particle of matter has an antimatter twin, opposite in charge, and since the neutrino has no charge, a suspicion arises that is unique in all of physics. Perhaps the neutrino and the antineutrino are not twins at all. Perhaps they are the same particle, a substance that is its own mirror image, a possibility named after the Italian prodigy Ettore Majorana, who proposed it in the 1930s and then, in one of science's enduring mysteries, boarded a ship in 1938 and vanished without trace, leaving the question as his monument. It sounds like a technicality. It may be the answer to the largest question there is, because the deepest unsolved problem in cosmology is the problem of why anything exists. The Big Bang, by every rule we know, should have minted matter and antimatter in exactly equal amounts, and equal amounts annihilate perfectly into light, leaving a universe of pure radiation with no stars, no planets, and no one to be puzzled. Instead, for every billion particles of antimatter, the young universe somehow held 1,000,000,001 matter, and that one part in 1,000,000,000 surplus, after the great annihilation, is everything, every galaxy, every ocean, every person. Something tilted the balance, and decades of searching have shown that ordinary particles cannot tilt it anywhere near enough. The neutrino is now the prime suspect. If it is its own mirror image, and if, as several experiments have begun to hint, neutrinos and antineutrinos oscillate in subtly different ways, then in the universe's first moments, the decays of their heavy primordial relatives could have leaked the crucial surplus of matter, a mechanism physicists call leptogenesis. Understand what is being said. The particle that cannot touch you, the ghost that a light year of lead cannot stop, may be the reason there is anything to touch at all. Your existence, in this scenario, is the neutrino's fingerprint. The experiments that will test this are running and rising now. Giant chambers searching for a never-observed decay that only a Majorana neutrino permits, and two colossal next-generation oscillation projects, one firing a neutrino beam 800 miles through the body of the Earth, from Illinois to a mine in South Dakota, Davis's old haunted ground, the other in Japan, a tank dwarfing even Super Kamiokande, both built to measure, at last, whether the ghost and its mirror dance to the same tune. Within the lifetimes of most people watching this, the question of why there is something rather than nothing may receive its first experimental answer. And if it does, the answer will have come from the particle nobody wanted, invented in an apology, in a letter, as a desperate remedy. No honest biography hides its subject's scandals, and the neutrino has one, a proper international scandal, and it is worth telling in full, both because it gripped the world for 6 months and because its ending is one of the finest lessons in how science earns trust. In September 2011, a respected experiment called Opera, which fired a beam of neutrinos from the CERN laboratory near Geneva through 730 kilometers of solid rock, straight through the body of the Earth, no tunnel required or possible, to a detector under a mountain in Italy, announced a measurement that made headlines on every continent. Their neutrinos, timed with atomic clocks and located with satellite positioning, appeared to be arriving early, 60 billionths of a second early, which meant, if true, that the neutrinos were traveling faster than light. You may remember the fever. Faster than light means, in Einstein's universe, the possibility of effects preceding causes, messages to the past, the collapse of the deepest rule of order in physics, and for one strange autumn, respectable newspapers were interviewing physicists about time travel. What matters for our story is what the Oprah scientists themselves did, because it was the opposite of triumphant. They spent months privately hunting their own mistake, rechecking every cable and clock, and only went public, with visible reluctance, to ask the worldwide community to help them find the error they could not find, releasing every detail of the measurement for inspection. Rival experiments prepared to test the claim independently. Theorists pointed out, elegantly, that a faster-than-light neutrino should shed energy in flight in a way the beam showed no trace of, and, most beautifully, that we already possessed a rebuttal from nature itself, the neutrinos of supernova 1987A, having raced the light of the explosion across 168,000 light-years, arrived hours early, not the 4 years early that Opera's speed excess would demand. Over a journey 1,000,000,000,000 times longer than the run from Geneva to Italy, the ghost had kept perfect pace with light's limit. And then, in early 2012, the culprit was found, and it was almost unbearably mundane: a fiber optic cable carrying the satellite timing signal, whose connector was not fully screwed in, loose by a whisker, delaying the clock signal, manufacturing 60 billionths of a second of false earliness. The connector was tightened, the measurement repeated, the anomaly vanished, the neutrinos flew at exactly the speed they were always supposed to fly, and the leaders of the experiment resigned their posts, as leaders in that culture do when a claim of that magnitude fails. It is tempting to read the episode as an embarrassment. Physicists largely read it the other way. The system had worked in public, at full transparency, an extraordinary claim, openly submitted for demolition, tested against independent experiments and against a supernova's own testimony, traced to its humble cause, and corrected, all within a year. The ghost, for its part, emerged with its reputation enhanced, its speed now confirmed to exquisite precision by the very scandal that questioned it. And physics had given the world a rare, live demonstration of the difference between a field that wants to be right and a field that checks. And since we have seen the ghost-saving laws, opening stars, and surviving scandals, it is fair to ask the practical question: is this creature good for anything? Can something that ignores all matter ever be useful to creatures made of it? The answers, arriving in this century, are a quiet delight. The first is already real: reactor monitoring. A nuclear reactor's neutrino glow is involuntary. It cannot be shielded, faked, or hidden, because nothing stops neutrinos, and its precise character reveals what is happening in the core, including the telltale signatures of plutonium production. Detectors the size of a car, parked outside a reactor building, have demonstrated they can watch a reactor's inner behavior in real time, through the walls, and international agencies have studied them as incorruptible inspectors for nuclear treaties, safeguards enforced by the one messenger that cannot be bribed, blocked, or lied to. The second is geology, on the grandest scale. We have already met the geoneutrinos glowing up from the Earth's radioactive interior. Measured carefully, they take a census of the planet's uranium and thorium, constraining how much of Earth's inner heat is radioactive in origin, one of the oldest questions in geophysics, answered by ghost light from the mantle. Further ahead, physicists have mapped out neutrino tomography, because ultra-high energy neutrinos are very slightly absorbed by extreme amounts of matter, the way Ice Cube sees the northern sky dim at the highest energies through the planet's core. The Earth's interior density can be imaged from the inside, an X-ray of the world using the sky as the lamp, and the first crude measurements of the planet's mass profile by this method have already been published. And in 2012, in an experiment that reads like a stunt and is actually a milestone, researchers at Fermilab used a neutrino beam to send a message through 240 meters of solid rock. The beam was pulsed in code, a detector on the far side read the pulses, and the decoded message, transmitted through the ground itself, through material no radio wave could cross, was a single word: neutrino. The bitrate was absurdly slow, and the machinery absurd, and none of that is the point. The point is the precedent: communication through the body of a planet, through oceans to submarines, someday perhaps across the shadowed cores of solar systems, using the one carrier for which the universe has no walls. The ghost that spent its first decades defined by uselessness, by its refusal to touch our world, is being slowly domesticated into the most incorruptible messenger, inspector, and cartographer we possess, And the engineering has only begun. There is one more open chapter, and it concerns a rumor within the family, the possibility of a hidden sibling. I told you the collider measurements closed the family at 3, and that is true, but read the fine print. The measurement counts 3 neutrinos that feel the weak force, 3 siblings who answer the one telephone the ghost owns. It says nothing about a relative who answers no telephone at all. Physicists call this hypothetical fourth kind, the sterile neutrino, a neutrino deaf even to the weak force, touching the universe through gravity and through nothing else, detectable only indirectly, if the ordinary ghosts occasionally oscillate into it and seemingly vanish from our counts. It sounds like a particle designed to be unfalsifiable. Pauli's terrible thing all over again, one floor further down, and yet the idea refuses to die. Because for 3 decades, a series of experiments has recorded small, stubborn anomalies, appearances and disappearances in neutrino beams and reactor measurements that do not quite fit the 3-flavor picture. Hints that flare, fade under scrutiny, and flare again in the next experiment. The anomalies may all be mundane, and several have already partially dissolved under better analysis. The field is divided and cheerfully bad-tempered about it, but the stakes explain the persistence. A sterile neutrino, if heavy enough, is a natural candidate for at least part of the universe's dark matter, the unseen mass whose gravity we charted on another night. Certain versions could be watched for as a faint X-ray whisper from the centers of galaxies, and tentative claims of exactly such a whisper have come and gone from the journals. If that identification ever firmed up, the arc would be almost too perfect. The particle family that saved the law of energy, explained the sun, and may have authored the survival of matter, also supplying the hidden scaffolding of the galaxies. It would be, in the truest sense, the ghost's family business. No one should bet the house on it, but no one who knows this particle's biography ever again says the word impossible with full confidence. Its entire life has been a sequence of things that could not be done, a particle that could not exist, then could not be detected, then could not have mass, then could not point to its sources across the universe. Every wall it was told about, it walked through. That is not mysticism. Every step was forced by measurement, checked by rivals, and paid for in decades of patience in deep mines and frozen ice. But it does explain the particular tone physicists use when they talk about neutrinos. A tone reserved for the colleague who keeps quietly turning out to be right. And before the closing pages, one scene from the biography deserves to be restored in full, because I passed over it quickly, and it may be the single most astonishing act of patience in the whole story, the keeping of the watch for the next nearby supernova. The 24 ghosts of 1987 were caught by accident, by detectors built for other purposes. Today, the watch is deliberate. A worldwide network called SNEWs, the Supernova Early Warning System, links the great neutrino detectors on 3 continents into a single tripwire, listening around the clock for the signature no other instrument can hear. The 13-second flood that announces a star's core has collapsed, hours before any telescope can see the explosion breach the star's surface. When the next giant star dies in our galaxy, and the averages say we are due, the neutrinos will arrive first, exactly as they did in 1987, and this time humanity intends to be ready. The network will triangulate the direction and issue an alert to every observatory on Earth. And for the first time in history, astronomers will be watching a star at the moment its light of destruction first emerges, tipped off by ghosts. The detectors of this era are so much larger than those of 1987 that a supernova at the center of our galaxy would deliver not 24 events, but hundreds of thousands. A second-by-second film of a stellar core in its dying moments, the most intimate recording of a cataclysm ever made. There are astronomers who have spent their entire careers maintaining this watch without receiving a single alarm, tending tanks and mines for a signal that may come tomorrow or in 50 years, and they describe the duty without complaint, because they understand what the first alarm will be worth. Somewhere in our galaxy tonight, a star is within decades of that 13-second flood. Its announcement is already inevitable. The mailboxes are open, the watch is kept, and when the message comes, it will pass through you on its way to the instruments, trillions of ghosts carrying the news through your sleeping body a few hours before the new star blooms in somebody's sky. So let us close the biography the way biographies close, with the arc of the life entirely. Born in December 1930, in a letter that began, "Dear radioactive ladies and gentlemen," as a bookkeeping trick to save physics' most sacred law, its own father calling its invention a terrible thing and betting champagne against its capture. Named in Rome, the little neutral one. Caught in 1956 beneath a nuclear reactor by hunters who called their work poltergeist, and toasted in Zurich by the man who apologized for it. Sent, in the decades after, down into gold mines and up against the sun, where its strange shortfall spent 30 years as a crisis before revealing, in a mountain in Japan and a mine in Canada, that it changes identity in flight, that it has mass, and that the grandest theory in science is unfinished. Witnessed, in 1987, carrying the death notice of a star through every person on Earth 3 hours ahead of the light. Frozen into a cubic kilometer of Antarctic ice and taught to point at black hole jets 4 billion light-years away. Revealed as the second most common particle in the universe, as the oldest unaltered relic of the first second, as a resident of your own body's chemistry several thousand times per second, and as the possible author of the surplus that let matter survive its own creation. Not bad for a particle that cannot be detected. And here's the thought I want to tuck in beside you as the night settles. We are accustomed to measuring importance by force. The loud things, the bright things, the things that push back when pressed, those, we assume, are the things that matter. The neutrino is the universe's standing correction to that assumption. It is the gentlest thing that exists, a particle so mild that the word touch barely applies to it, and yet it saved the law of energy, opened the heart of the sun, announced the deaths of stars, cracked the standard model, and may yet explain why there is a universe rather than a perfect, silent cancellation. All of that accomplished by the faintest possible whisper, repeated patiently, quadrillions of times a second, for 13.8 billion years. As you lie there now, the rain is falling through you. 65 billion per second through your thumbnail, from the sun beneath the world. Millions of relics of the first second drifting through the room, a few thousand per second, leaving your own body, beginning journeys that will outlast the earth. None of it will ever hurt you. Almost none of it will ever touch you. Once every year or two, a single ghost will brush a single atom of you, the lightest kiss in nature, and continue on its way to forever. You have never been alone for 1 second of your life, and you have never once been disturbed. That is the neutrino's whole biography, and it might be the kindest fact in physics. If tonight's story kept you in good company, a like or a subscribe genuinely helps this channel keep telling them, and it means more than you know. The universe will still be strange in the morning. Good night.